Congruent non-overlapping circles A, B, C, and D are positioned in a plane such that A, B, and C are mutually tangent to each other, and circle D is tangent to circle C. Triangle EGF circumscribes the four circles as shown. What is the length of side FG? And you probably noticed my haircut. And fun fact, me and my dad, we have the same hairstyle because our mom, she cut her heads both, so she cut them the same, nice and round. Hopefully you noticed that too, a round head. And if you put me and my dad in a picture with a whole bunch of other people, you could tell just right away that me and my dad, that he was my dad and not some other person in the picture, because we had the same hairstyle. Okay, so anyways, this problem, we're first going to talk about what tangent means and what circumscribe means. Well, tangent is just for circles. It only talks about circles, so I'm going to just draw a circle to talk about the tangent. So, pardon me. Tangent just means that only one point of the circle touches something else. It can be a 2D shape, a 3D solid, or just a line. So, using that definition, you'll see that this is a line tangent to this circle. Now, this is not tangent. This line right there, it's not tangent to the circle because it touches 2 points on the circle. So basically, it can't go inside the circle, because once it goes inside the circles, the minute it exits, it will hit a point, a boundary point on the circle, which will be the second time it touches the circle, meaning it will not be tangent to the line. Also, this is not a line tangent to the circle because even though it looks like there's only one point that touches the the circle itself, well, remember, the line, in the real geometric term of the line, it goes forever in both directions. So we'll continue this forever and ever and ever, and then we'll see that there's are still 2 points that touch the circle, and obviously this is not a line tangent to the circle. It's not even touching the circle, meaning it can't be tangent to it. And this line that is tangent to the circle, well, if we continue it forever, well, it still won't touch any other points of the circle. It's already well past the circle, so that's what you call a tangent, a line. So now we can talk about circumscribes. And you can probably guess that, by the way, circumscribes just sounds like circle, that it has something to do with the circles, and it does, and you are right. It only talks about circles, just like tangent. So for circumscribes, it just means that, well, it's hard to explain. It's more like something you just know. So, well, how about just start like this? Circumscribes, it just means it means a lot like contains, but it's not just any type of contain, because usually contain, like if we say this triangle contains a circle, well, we don't tell you where physically the circle is, so circle can be here, or it can be here. But when you say circumscribes, it means that the circle inside is tangent to the tangent to this whatever contains the circle, because we are talking about circles. So for example, this is an example of the circumscribe idea, because the circle is tangent to every one of these lines, and it's basically the same thing here, only a bigger version. every circle is tangent to at least one of the edges of the triangle. So that's what circumscribes means. So now, finally, we can dive into the problem. Now we are given that the radius of this is 1. We'll see how that affects us later on, but the trick I see is that whenever I see these tangent circles, I like to connect their centers, because whenever I do that, you'll see eventually, well, and I'll tell you that when I get to it. So anyways, I'll keep this promise. I'll tell you why I like to connect these centers. Okay, so anyways, now we have these. Let's draw the radii to the point of tangency on this triangle. What I mean by that is draw the radii so that they make right angles. And you know why I want right angles? They just usually give you good stuff like, I don't know, squares and rectangles, but there's probably more to it than that. Okay, let's finish drawing these. Okay, we have one down from C and one down from D. Oh wait, and I also forgot to connect A to D. Remember, we are connecting all of the centers of our circles. Now, okay, this is this angle a little more natural. Well, hey, wait a minute. This little shape in the middle, well, it has 2 right angles, and this right here, that's 1 radii. This is 1 radii. Both of these are 1, so this is 1, this is 1. Well, that means this little shape in the middle, that's a rectangle. And because this is 1 radii, this is another radii, this whole thing in the middle, AB, that's 2. So that means this length right here is 2, and that's like part of the reason why I like connecting these centers, because like they just tend to give you good things like right triangles, and here it's rectangles, so you can find side lengths on the outside of this triangle. So that's basically the first thing I do when I see tangent circles, connect their centers. Well, do the same rectangle business with all these other rectangles. So this is 2 because of these 2 radii. And this is 2 because of these 2 radii. And I don't know what to do with this rectangle, so we'll leave that alone. Okay. Well, in the middle, I see this triangle shape, and well, you know, AB and BC and AC, we know that's a straight line because, well, mostly, like, you don't need to know if this is a straight line or not, because usually problems, like, don't get, like, this precise to the, like, point where you have to, like, calculate if this is a straight line or not, but it's still good to know, just in case it pops up. But it's also just, well, you just need, like, sometimes you just need a lot of reasoning like this to solve problems, so it's not, like, terrible to see if this is a straight line or not. So, well, if you think about it, whenever we have 2 tangent circles, whenever we connect their centers, well, tangent circles, well, they mean that there's only one intersecting point of the circles. So, well, what I mean in straight line is, well, how do we, you might be thinking, well, what does that have to do with, like, making sure that the center of the circle and the center of the circle and this little point of tangency in the middle, how do we make sure that these are all in a straight line? How does this tangent definition help us with that? Well, because of that, well, if these 3 points, if they weren't in a straight line, well, then the circles won't be tangent, right? They will have to like go through a teeny itty bitty gap in the middle to reach the next circle and keep on going to the next center. Meaning this line has to go through this point of tangency in the middle, which will make sure that AC is a straight line. And if we do that reasoning of AB and BC as well, we'll see that all of these edges of this triangle, which we proved is a triangle itself, all of these sides are straight lines, and more importantly, more interestingly, it's an equilateral triangle, right? Because each of these side lengths are just 2 radii. Okay, so now that we know that these are equilateral triangles, we can go ahead and mark in some angle measures here and there. And well, we know BD is a straight line because, well, every point on this line is 1 radii or 1 unit above FG, so BD is a straight line. Meaning, because we have 60 degrees here, we will have 120 degrees there. Put in degrees mark. Well, AC is 2 radii, so, and CD is also 2 radii, so AC and CD, they're equal. So triangle ACD, that's an isosceles triangle, so we have 120 degrees here, meaning these two angles are 30 degrees, because again, triangle has 180 degrees in all if you add the 3 angle measures. Okay, so now, wait a minute. 30 degrees, 60 degrees. Well, we should look for 30, 60, 90 triangles. Well, we have a 30 degree, 60 degree, and well, 30 plus 60, that just makes a 90 degree angle, or right angle. Meaning, this is a right angle, 60 degrees, 30 degrees. ABD, that is a 30, 60, 90 triangle, and oh, EFG looks awfully similar to ABD, and by similar I mean the exact topic that if you just expand this triangle a little bit, you get this big triangle. I am using the exact definition of similar triangles. Okay, so now I just need to prove that EFG is a 30, 60, 90 degree, 30, 60, 90 triangle, and if we do that, we'll probably be able to get down to how we'll be able to get FG. I'm getting a little ahead of myself, but anyways. Well, now we see that we have a little more information. We can find what this little side length is, because we have a 90 degree angle here, and because this is a rectangle, this is a right angle, and because of this little rectangle over here, this is also a 90 degree angle. Okay. This is getting very, very messy. I wish I drew a larger diagram. Well, we got 3 of these 90 degree angles. That means this is also a right angle. So we have 3 right angles here. Means this, the little puppy right there, that's a square with side length 1. That's the radii. So this is side length 1. Okay. Well, now I can go back to trying to prove that this is a 30, 60, 90 triangle, because we already have the 90 degrees. So we just need to find angle F or angle G to figure out if this large triangle is a 30, 60, 90 triangle or not. And I'm betting that it is. So, well, I'm going to focus on angle F, see if we'll be able to figure out how much degrees that is. Well, let's see. This is a right angle from this rectangle, and this is also a right angle from this rectangle. So we have 2 right angles, and that's 180 degrees in total. one full circle is 360 degrees, minus 180 is another 180 degrees. So that means this angle over here plus this angle over here, that means those two have to sum up to 180 degrees. So we already have a little 60 degrees taken away, meaning this big angle out here, that's 120 degrees. And I almost said degrees Celsius. So, anyways, well, we can basically do the same thing here to find out what angle F is, because we already have two right angles, and well, that's 180 degrees again. And if you add all the angles up in a quadrilateral, which is exactly what this shape is, well then you get 360 degrees again. So again, we take away the 180 degrees, we have another 180 left, and then we have a good chunk, a good 120 degrees taken out of that. Meaning, yep, sure enough, angle F is 60 degrees, meaning angle G is 30. So now we prove that this is a 30, 60, 90 triangle. So now I just need to figure out either EF or EG, and then we'll know what FG is. Okay, now I'm going to focus most of my attention on segment EF, because we're almost done figuring out how long that is. You just need this little chunk right here. Can we figure that out? Hey, more 30, 60, 90 triangles. We cut this in half, and we see that this is at half because we see well, this angle is 90 degrees and this angle is 90 degrees, so we have kind of a symmetry, and cut that symmetry in half. Well, then we do get two identical 30, 60, 90 degrees. And well, if you look at it, well, it's kind of like a jet, right? If you like outline the shape, like that's kind of like the cockpit, and then there's like that little tail thing over here. It's an equilateral triangle. If you think about it, it does look kind of like a sparrow or a jet or something cool, but I can't put my hand on it. Well, I can't exactly get the idea of what it actually is. Maybe I'll be able to figure out when I'm older. But anyways, today is not the time. So, well, this is a radii, so that's 1. And, well, that's the short leg of of a 36 90 triangle, and the long leg is just the short leg times root 3. So 1 times root 3 is root 3. So now we know that this entire thing is just 3 plus root 3. Okay, and wait a minute. Think about it, just tilt your head a little bit, or just tilt your monitor a little bit. It kind of feels like a 30, 60, 90 degrees. Hey, I wish they just lifted this up a little bit. Okay, these guys kind of get pretty mean, but anyways. So, okay, well, we have this length, so that's the short leg of this 30, 60, 90 triangle. And this long leg, well, the relationship of the long leg to the short leg is just 1 to 2, meaning this FG is just double EF, and double EF is 6 plus 2 root 3.